In late February 2026, somewhere inside a routine command sequence that engineers at NASA's Jet Propulsion Laboratory had run 1,000 times before, something started to go wrong on a spacecraft that was already 25 billion kilometers from Earth. Voyager 1, the oldest, farthest, and most fragile machine humanity has ever built, was performing a simple roll maneuver, a small rotation used to calibrate its instruments, when its power levels suddenly dipped without warning. For a few tense hours, mission controllers watched the numbers edge dangerously close to a threshold that would have triggered something called an undervoltage fault, an automatic self-preservation mode that shuts down critical systems the instant power drops too low. If that fault had triggered, Voyager 1 would have gone quiet, and getting it talking again would have meant weeks of recovery, with every command taking almost a full day just to arrive. The spacecraft didn't die that day, but the scare was enough to force NASA's hand. On April 17, 2026, engineers sent a command across 23 hours of empty space and permanently shut down the low-energy charged particles experiment, an instrument running almost without interruption since Voyager 1 launched nearly 49 years earlier. It was one more piece of a 1970s machine going dark forever, one more sacrifice made just to keep a heartbeat going. And yet, right now, that same failing, freezing, half-blind spacecraft is still doing something almost impossible to believe. It is still listening. It is still receiving signals from a region of space no human being will ever personally visit, translating an environment nobody expected to have a voice at all, and sending that information back to a planet it left behind almost half a century ago. This is the story of how a machine running on less power than a refrigerator light bulb became the only working set of ears humanity has ever had in interstellar space, and why 2026 might be the year we finally learn whether it can hold on long enough to keep listening. When Voyager 1 lifted off on September 5, 1977, nobody involved in building it expected any of this. The mission plan was almost embarrassingly modest by comparison to what actually happened. Fly past Jupiter, fly past Saturn, take pictures, gather data, and finish the job in about 5 years. That the spacecraft is still transmitting from beyond the edge of the solar system 50 years later was never part of the design. The only reason the mission's actual trajectory was even possible came down to a rare alignment of the outer planets. A configuration that lines up roughly once every 175 years, placing Jupiter, Saturn, Uranus, and Neptune all on the same side of the Sun. Engineers realized they could use each planet's gravity to fling a spacecraft toward the next one, a path they nicknamed the Grand Tour. Voyager 2 actually launched first, 16 days before its twin, but Voyager 1 was placed on a faster trajectory and quickly overtook it. 13 days after launch, from more than 11 million kilometers away, Voyager 1 turned its camera back toward home and captured something nobody had ever recorded before. Earth and the Moon together in a single frame, our entire planet reduced to a small, fragile point of light floating in darkness. By early 1979, Voyager 1 reached Jupiter, and what it found tore apart decades of assumptions built from ground-based telescopes. This wasn't a calm, static gas giant. It was a violent world wrapped in storms, laced with punishing radiation and surrounded by moons that behaved almost like a miniature solar system of their own. The spacecraft detected faint rings nobody had known existed, and photographed the Great Red Spot up close for the first time, confirming it as a storm larger than Earth itself, still raging after centuries. But the real shock came from Io, one of Jupiter's 4 large moons. Voyager 1 caught active volcanoes erupting on its surface, the first time humanity had ever witnessed volcanic activity beyond Earth. Io wasn't dead rock drifting in the dark. It was violently, geologically alive, and to this day it remains the most volcanically active body known in the solar system. Nearby, Europa's cracked, icy shell hinted at something even stranger, a hidden ocean of liquid water sealed beneath kilometers of ice, an idea that quietly reshaped the search for life beyond Earth. Suddenly, the best place to look for life wasn't necessarily a planet, it might be a frozen moon orbiting one. After Jupiter flung it forward, and Voyager 1 reached Saturn in November of 1980, carrying more speed than any human-made object before it. What had looked from Earth like one simple ring turned out, up close to be hundreds, even thousands of separate shifting bands. New moons appeared in the data, including one called Mimas, whose enormous crater gave it the unsettling look of a small battle station. But the mission's most consequential decision happened here, when engineers chose to send Voyager 1 close past Titan, the moon with the thickest atmosphere in the solar system. The flyby revealed that Titan's atmosphere behaved in ways nobody expected, with methane taking the place water occupies on Earth, existing as a solid, a liquid, and a gas, hinting at lakes and rivers on a world far colder than our own. That single flyby permanently altered the mission. Saturn's gravity bent Voyager 1's path sharply out of the flat plane where the planets orbit, meaning it could never visit another world again. From that instant forward, Voyager 1 stopped being a planetary explorer. It became something else entirely, a machine with nowhere left to go but out, accelerating toward the edge of everything the sun could reach. Before any of that outer system drama unfolded, engineers back on Earth had already made a decision that had nothing to do with orbital mechanics at all. Bolted to the side of each Voyager spacecraft is a golden phonograph record about the size of a dinner plate, holding a carefully assembled portrait of life on Earth. It carries greetings recorded in 55 different languages, natural sounds like thunder, wind, and whale song, more than 100 images encoded as data, and 90 minutes of music spanning continents and centuries. A small team that included astronomer Carl Sagan championed the idea, betting that a 5-year mission was still worth attaching, a message meant to survive essentially forever, built for whoever or whatever might find it long after everyone involved in launching it was gone. Then came the long, quiet stretch, years of travel through what looked, from Earth, like empty space. And on August 25th, 2012, Voyager 1's instruments picked up something nobody fully expected. A sudden sharp drop in charged particles streaming outward from the sun, paired at the very same moment with a spike in high-energy particles arriving from deep in the galaxy. It wasn't a slow fade. It happened almost like the spacecraft had physically struck an invisible wall. Voyager 1 had crossed the heliopause, the boundary where the sun's influence finally gives out and true interstellar space begins. For decades, scientists had modeled this region as a gentle, blurry gradient, something a spacecraft would drift through gradually over weeks. The real data told a different story. Charged particle counts collapsed within hours, not weeks. The boundary behaved less like a fading edge and more like an actual membrane, a place where two distinct kinds of plasma, one shaped by our star and one shaped by the galaxy, meet and resist blending together. It became one of the most cited surprises in the mission's history, forcing physicists to rebuild long-held models of how stars interact with the space around them. And here is where the story stops being about a boundary and starts being about a signal. Crossing that wall didn't just tell scientists where Voyager 1 was, it revealed that the space between stars is not silent. For more than 24 billion kilometers away, Voyager 1 picked up a steady, low hum sitting at around 3 kilohertz, a tone that lasted for close to 3 years. Researchers described it as something like a thin, metallic ring, as though the emptiness between stars were quietly resonating in the background. That sound turned out to be interstellar plasma waves, oscillations, in the thin, charged material drifting between stars. By studying that hum, scientists could calculate the density of the material out there, turning an eerie tone into a working scientific instrument, a way of mapping something no telescope on Earth could ever directly see. At the same time, Voyager's readings showed that the interstellar magnetic field pressing against the heliosphere was 2 to 3 times stronger than any model had predicted, exerting nearly 10 times more pressure than expected. That discovery meant our entire solar system sits inside a tightly compressed bubble, actively shaped and squeezed by the surrounding galaxy, rather than floating freely in open space the way most people had always imagined. Voyager's data also helped confirm something called the local bubble, a cavity roughly 1,000 light-years wide, carved out by ancient supernova explosions long before humans existed, a structure that has been quietly shielding our solar system from interstellar dust and cosmic radiation this entire time, without most of us ever realizing it. Voyager 2 crossed that same boundary 6 years later, in November of 2018, at a different point along the heliopause, giving scientists a second independent measurement of the same structure from an entirely different angle. Comparing the two crossings revealed that the heliopause isn't a smooth, perfectly round sphere surrounding the sun. It's closer to an irregular, dented shape, pushed and pulled unevenly by interstellar wind blowing from one general direction as the sun moves through the galaxy. 2 data points, gathered years apart from 2 different locations, turned one strange reading into a confirmed feature of our solar system's actual outer shape, something no telescope on Earth could ever have measured alone. Which brings the story to right now, to 2026, and to a spacecraft that is running dangerously close to empty. Voyager 1 currently sits somewhere around 25.5 billion kilometers from Earth, more than 170 times the distance between Earth and the Sun. And it is still moving outward at roughly 17 kilometers every single second. A radio signal now takes close to 23.5 hours to travel one way between the spacecraft and mission control, which means a single command sent up and confirmed back consumes nearly 2 full days. NASA has calculated, down to the exact second, that on November 18th, 2026, at 2:16 and 7 seconds in the morning Pacific time, Voyager 1 will cross a genuinely historic line, becoming the first human-made object to sit a full light day away from Earth. At that precise moment, the spacecraft will be 16,799,096 miles from home, a distance so vast that light itself, the fastest thing that exists anywhere in the universe, needs a full 24 hours just to cross it. To put that number in perspective, Voyager 1 at that milestone will be roughly 5.5 times farther from Earth than Neptune, and yet in its entire 49-year journey to get there, it will have covered barely a few thousandths of 1% of the distance to the nearest star beyond our own sun. But reaching that milestone is costing the spacecraft nearly everything it has left. Both Voyager probes run on radioisotope thermoelectric generators, devices that convert heat from slowly decaying plutonium into electricity. That power source has been fading by roughly 4 watts every year since launch, a slow, silent drain that can never be reversed. As of early 2026, both spacecraft are producing less than half the power they generated the day they left Earth. To stretch the mission for as long as physically possible, engineers have had to shut down instrument after instrument in a carefully chosen order, sacrificing pieces of the spacecraft's senses one at a time just to keep its core alive. Voyager 1's cameras went dark back in 1990, right after capturing the mission's famous final portrait of the solar system. Its plasma science instrument stopped working reliably by 2007. Its ultraviolet spectrometer, which lasted far longer than most engineers expected, was finally switched off in 2016. NASA shut down Voyager 1's cosmic ray subsystem in February of 2025 to conserve what little power remained. Then, following that close call during the February 2026 roll maneuver that nearly triggered an automatic shutdown, engineers made the call on April 17, 2026, to permanently deactivate the low-energy charged particles experiment, an instrument that had quietly measured ions, electrons, and cosmic rays from both our solar system and the wider galaxy for almost 49 uninterrupted years. That leaves only 2 working science instruments still active on Voyager 1 in 2026, the magnetometer, which tracks the magnetic field surrounding the spacecraft, and the plasma wave subsystem, the very instrument responsible for picking up that eerie interstellar hum drifting in from beyond the sun's reach. Its twin, Voyager 2, had already lost its own version of the same instrument roughly a year earlier in March of 2025. NASA's mission team has been remarkably direct about what these repeated shutdowns actually mean. Powering down a working science instrument is never anyone's first choice, but for a machine running this close to its absolute limit, it remains the only realistic option left to keep the spacecraft alive. Engineers estimate that shutting down the low-energy charged particles experiment alone should buy Voyager 1 roughly 1 more year of stable operation, conveniently carrying it right up toward its own 50th anniversary in September of 2027. And engineers aren't simply watching the clock run out in the meantime, they're racing against it. NASA's team has been developing an ambitious software and hardware fix, nicknamed internally as the Big Bang, designed to squeeze far more efficient operation out of an aging, freezing spacecraft, and potentially even bring some previously shut down instruments back online for short stretches. The plan involves swapping out a cluster of powered components essentially all at once, turning some things off permanently while replacing others with lower power alternatives, all in an effort to keep the spacecraft's remaining electronics warm enough to keep functioning. The team chose to test this fix first on Voyager 2, which has a bit more spare power and sits closer to Earth, making it the safer test subject, with trials planned across May and June of 2026. If those tests succeed, engineers plan to attempt the very same fix on Voyager 1 no earlier than July of that year. If it works, there is even a real chance that Voyager 1's low-energy charged particles instrument could eventually be switched back on. It's an unusual kind of optimism for a machine pushing 50 years old, built with 3 onboard computers that share barely 68 kilobytes of memory between them, running on processors clocked at just 250 kilohertz, a fraction of the power inside a basic pocket calculator. Commands travel up to the spacecraft at a mere 16 bits per second, while scientific data trickles back down to Earth at around 160 bits per second, a data rate slower than an old dial-up internet connection. And every fragment of that data has to survive a journey through an environment sitting close to absolute zero, where cosmic radiation constantly threatens to corrupt whatever fragile circuitry remains functional after 5 decades of continuous exposure. The logic behind every one of these decisions comes down to a brutal trade-off. Engineers now face every single year, every remaining watt of power on Voyager 1 has to be split between 2 competing needs. Keeping onboard heaters running so delicate hardware and fuel lines don't freeze solid in the cold of interstellar space, and keeping the spacecraft's last remaining instruments powered up long enough to keep sending back readings. Shut down too many heaters too soon, and critical hardware could fail outright with no way to repair it from 25 billion kilometers away. Keep every instrument running a little too long, and the spacecraft could burn through its remaining power years earlier than necessary. NASA's own internal projections have suggested that without continuous conservation moves like the ones made in 2025 and 2026, Voyager 1 might have had only a handful of months of usable power left, before controllers would have had no choice but to declare the mission over. With this kind of careful watt-by-watt rationing instead, The team now believes at least one science instrument could realistically keep functioning into the early 2030s, stretching a mission originally planned for 5 years into one that could ultimately run for nearly 6 decades. Officials remain careful to note that any single unexpected hardware failure could still cut that timeline short without warning, exactly the kind of scenario that nearly played out during that tense roll maneuver back in February. Suzanne Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, has been honest about just how thin that margin really is. If the propellant lines on either spacecraft were to freeze, causing their antennas to drift even slightly away from pointing at Earth, the mission would effectively end within moments, since there would be no way to send a usable signal back to a receiver that isn't listening in the right direction anymore. The team's current hope is to keep the magnetometer and plasma wave subsystem functioning on both spacecraft, along with the surviving cosmic ray subsystem still active on Voyager 2, letting the two probes operate almost like a pair of weather stations scattered across interstellar space, quietly sensing an environment no human will ever personally reach, long after their cameras and most other instruments have gone silent for good. This fragile, patched-together survival isn't new either. The spacecraft has already faced moments that came close to ending everything. On November 14th, 2023, Voyager 1 suddenly stopped sending back anything intelligible, transmitting nothing but streams of garbled binary noise, a signal suggesting something deep inside its onboard systems had broken. Engineers eventually traced the fault to a failure inside the spacecraft's flight data system, one of the most critical components on board. Rather than accept the loss of a machine that had already outlived every original projection, the team attempted something extraordinarily risky, rewriting and relocating decades-old code into whatever healthy memory remained on the aging hardware, a process demanding surgical precision given that every single command took nearly a full day just to arrive, with another full day required before confirmation could return. The tense operation began on April 18th, 2024, followed by days of total silence that stretched nerves to the breaking point. Then, on April 20th, Voyager 1 spoke again. Engineers described the moment as watching the heartbeat of an aging space traveler start back up. Voyager 2 had its own brush with disaster months earlier, when a routine command accidentally tilted its antenna just 2 degrees away from Earth, nearly severing contact permanently, until a powerful signal from a tracking station in Australia restored the connection after 37 agonizing hours of silence. Moments like these reveal something important about what these two machines actually are. They were never simply hardware drifting through the dark. They're stubborn, aging explorers, fragile and persistent in equal measure, still pushing forward even as their voices grow fainter with every passing year. Proof that decades after their own designers expected total failure, they're still out there, still answering, still carrying a piece of human curiosity into interstellar space. Voyager 1 never physically collided with anything out there, but what it ran into may be more significant than any solid object ever could have been. It crossed a frontier with no wall, no marker, and no visible edge announcing its existence, and entered a region where the underlying rules of space quietly change. Beyond the heliopause, Voyager 1 discovered that interstellar space isn't empty, isn't silent, and isn't passive. It found pressure where scientists had expected open freedom, structure where they had imagined total emptiness, and a steady cosmic hum where they had assumed nothing but absolute silence. It revealed that our entire solar system lives inside a fragile, compressed bubble shaped by forces far older and far more powerful than our own sun, and that even the space stretching between stars carries real texture, density, and sound. All of it uncovered by a machine that was never built to survive this long, running on a power source weaker than a household appliance, guided by computers less capable than a basic modern calculator, and still, somehow, expanding what humanity understands about where we actually are. As Voyager 1 continues drifting outward toward the far edge of the solar system's outer shell, a journey that will take centuries just to begin reaching the Oort cloud and tens of thousands of years to fully cross it, it carries something with it that matters more than any single instrument reading. It carries a record of us, our voices, our music, our images, and a quiet declaration that we existed, that we wondered about what was out there, and that we dared to reach beyond the limits of our own small world. Whether anyone or anything ever finds that message is almost beside the point. What matters is that we sent it anyway. Long after Voyager 1's last instrument finally goes dark, sometime probably in the early 2030s if current power projections hold, the spacecraft itself will keep moving forward regardless. A small fragment of humanity traveling through the dark on our behalf, carrying nothing but momentum and memory into a future none of us will ever personally see. Researchers have even calculated that tens of thousands of years from now, Voyager 1 will drift within roughly a light year of a star called Gliese 445, still carrying the golden record along for the ride, still moving long after every trace of the mission's original purpose has been forgotten by anyone left to remember it. Think about what that actually means in practical terms, right now in 2026. Every single day between now and whenever Voyager 1's last instrument finally goes silent, a team of engineers back on Earth is choosing to spend real time, real budget, and real attention on a spacecraft most people assumed had stopped mattering decades ago. They're still parsing faint, garbled signals arriving nearly a full day late. They're still deciding which watt goes where, still testing new code for hardware that predates almost every piece of technology in your home right now, still gambling an entire software overhaul on a machine sitting 25 billion kilometers away where a single mistake can't be fixed by hand. That's not nostalgia. That's active, ongoing science, extracted one careful decision at a time from the very edge of everything a human-made object has ever reached. And it's happening in a decade when most public attention around space exploration is aimed squarely at newer missions, fresh spacecraft heading toward the moon and Mars, telescopes peering toward the earliest galaxies, private companies racing to build the next headline-grabbing rocket. Voyager 1 doesn't compete for that kind of attention anymore. And in a strange way, that's exactly what makes it worth paying attention to. It isn't trying to impress anyone. It's simply still out there, still working, still sending back whatever fragments of interstellar space it can manage to capture before its power finally runs out for good. There's also something worth sitting with in the fact that nobody alive today will ever know exactly how this story ends. Voyager 1 will likely go silent sometime in the next decade or so. Its last transmission arriving on Earth long after most of the engineers who built it have passed away. But the spacecraft itself won't stop moving. It will keep drifting outward for millions of years after that final signal fades, carrying that same golden record the entire way. A message in a bottle cast into an ocean so vast that finding it would take almost unimaginable luck. Nobody involved in launching Voyager 1 back in 1977 could have guessed it would still be teaching us new things about the universe in 2026, let alone that a 50-year-old spacecraft running on a fraction of a modern phone's battery would still be humanity's only working set of eyes and ears beyond the edge of the sun's influence. That, more than any single discovery along the way, might be the real story here. And on November 18th, 2026, at 2:16 and 7 seconds in the morning, when Voyager 1 crosses the one light day threshold for the first time in human history, it will still be out there, still listening, still receiving signals from a place no human being has ever been, and still, against every single one of the odds ever stacked against it, finding a way to tell us about it.